Hello, I'm Theodore Jemison.
And I'm Michael Smith, and our research project is modeling energetic O+ ions interacting with Titan's atmosphere. This research was done with our advisor, Dr. Darcy Snowden, through the Physics and Astronomy Department at Central Washington University in Emmitsburg, Washington. To start, Titan is one of Saturn's 62 moons and is the only moon in the solar system to have a significant atmosphere. For our research, we investigated energetic particles from Saturn's magnetosphere entering Titan's atmosphere. Here, particles heat, ionize, and dissociate neutral atoms. This process has implications on the chemistry of Titan's atmosphere and is directly related to the energy deposited by incident energetic particles. Unfortunately, the various ways in which these particles deposit their energy has been largely unexplored by computational models, despite a plethora of data from Cassini flybys. Therefore, in an effort to investigate energetic particle behavior, we made a 3D model of oxygen ions in Titan's magnetosphere to simulate how these ions might enter the atmosphere.
Yeah, so pretty much what we did, jumping down to the modeling methods section, is Dr. Snowden provided us with a 3D matrix of electromagnetic field values from Saturn's magnetosphere in the region surrounding Titan. We took those field values and used a fourth-order lunge-cutter numerical differential solving equation method to solve the Lorentz force law, a law which governs the motion of charged particles, to obtain their velocities throughout their trajectory. With the velocities in hand, we used an Euler-Kromer method to determine the particles' position from their velocities. In order to accurately describe oxygen ions in the region surrounding Titan, a series of constraints concerning charge, mass, density, and average temperature were implemented. The resulting values enabled us to use a Maxwellian velocity distribution to obtain initial speeds. Particles were then given random starting positions outside of the ionosphere and random initial directions associated with the thermal excitation. Adding in the bulk motion of the magnetosphere relative to Titan allowed simulations of at times over 10,000 particles to be scaled up to reflect actual oxygen ion densities. This figure shows Titan, as well as the magnitude of the polar-aligned magnetic field near Titan. The red region reflects near-zero field values, while the blue region reveals the strongest antipolar line values. Saturn is located to the left in this figure, and the plus Z axis is in line with Titan's north pole. Further, Titan's motion is out of the page. The red region, which extends behind Titan, is known as the wake, while the blue region in front of Titan is called the pileup region. It is here that the magnetic field is at its strongest. The particles starting in or near the pileup region are deflected around Titan with a chance of impacting the atmosphere. Particles around the wake are deflected away from Titan. It can also be seen that ions collectively move away from Saturn due to the radial electric field.
The electromagnetic field values used by our model were generated by a 3D multi-fluid simulation of Saturn's magnetosphere near Titan, which was produced by Dr. Snowden. Here's a picture from her model, which shows the pileup regions as well as the wake. Her model takes into account factors such as ion production through various mechanisms and ion loss.
These two figures show the power flux incident on Titan's exobase. The exobase is the boundary between the exosphere and the ionosphere, the two outermost layers of Titan's atmosphere. The two figures illustrate the fact that particles enter the atmosphere on the pileup side of Titan and strike preferentially on Saturn-facing side due to radial electric fields. The average power flux on the incident side is reflective of incident O+ ions with energy in the kiloelectron-volt range.
From the power flux incident on Titan's exobase, we obtain two histograms. The first, which characterizes instant energy into the atmosphere, shows a quasi-Maxwellian distribution. This is to be expected as we initialized our velocity using a Maxwellian distribution. The second histogram characterizes instant angles into Titan's atmosphere. The graph shows particles enter grazingly, which means the O+ ions deposit less energy than if they were to enter the atmosphere normally. The final result of our research is an energy deposition rate for oxygen ions in the atmosphere of Titan. A maximum deposition rate of 10 electron volts per centimeter cubed times seconds occurs at an altitude of 1350 kilometers. The next step for our research is to include the contribution of atmospheric collisions with H2 molecules, which have recently been found to have an effect on particle deposition in the upper atmosphere. We then plan to compare our model to data collected by Cassini's ion-neutral mass spectrometer during flyby T57 in order to validate our model.
This research was supported by NASA grant NNX14AH81G, the Ronald E. McNair Post-Baccalaureate Achievement Program Summer Research Associate Internship, as well as Central Washington University. Thank you for watching. We hope you've enjoyed our presentation and learned a little bit about Titan.